So we will get started. Last lecture, we started talking about PCA. I mentioned that PCA stands for Principal Component Analysis, and it's a technique that is used for data approximation or data reduction. And through PCA, you can reduce the number of dimensions while approximating the data. And obviously, when you reduce the number of dimensions, there is going to be some loss of data or information in some sense. But PCA is a technique that tries to keep that loss as small as possible. All right. So let's look at some math, little bit of math related to PCA. So let us assume that we have capital N data vectors, and each data vector has n dimensions, where we are talking of a small n. So a small n is the number of dimensions. Capital N is the number of data vectors. So what we can do is we can use a linear transformation to apply principal components. So basically, PCA is obtained through a linear transformation, and that transformation is defined in this particular equation that you see, y sub I. So y sub I is the transformed vector corresponding to x sub I. And y sub I is obtained as matrix A multiplied with x sub I minus m of x. And this is true for every I in your data collection. So I ranges from 1 to capital N, where capital N is the number of different vectors that you have. What is this mx? Mx is really nothing but the mean of data vectors. All right. And A is a matrix that we use in the transformation to get the principal components. And the matrix A is formed using rows that come out as eigenvectors of the sample covariance matrix. So basically, what we are showing in this equation is that if you have a matrix A formed in a particular fashion, then you can use that matrix A to apply PCA or to do the transformation from X domain to Y domain. Now, how do we define sample covariance matrix? The formula for sample covariance matrix is shown here. So basically, it will be 1 divided by capital N minus 1. And then you take the product xk minus mx multiplied with xk minus mx transpose. So that gives you a matrix of size n by n. And you do this over all the examples. So basically, you can say you will get capital N number of matrices, which you add them up and then divide the result with 1 by n minus 1, and that will give you the sample covariance matrix. So once you have the sample covariance matrix, what we do is we calculate the eigenvectors and eigenvalues corresponding to the sample covariance matrix. And once you have those eigenvectors, you take a look at the eigenvector that corresponds to the largest eigenvalue. And you take that eigenvector and make it as a first row of your matrix A. Then you take the second eigenvector, which corresponds to the next largest eigenvalue, and put that in the second row, and so on and so forth. All right. At the bottom of the slide, you can see two equations, which basically give you the components of the covariance matrix. So the first equation, CPP, gives you the diagonal components, and the second equation gives you the non-diagonal terms or non-diagonal components. All right. So once you have the eigenvectors, you have formed your covariance matrix, and then you can apply the transformation as I showed you earlier. All right. So let's look at this equation of transformation in a vector matrix notation form. So you can say, all right, we apply this transformation, and let us calculate what is the covariance matrix in the transformed space. So you have an X space, which is your starting space. And through transformation, you get a new space, which you call as a Y space. All right. So let us assume that we have applied the transformation. We got all these Y vectors. And now we calculate the covariance matrix for these Y vectors. If you do a little bit of math, you will find that the covariance matrix in the transformed space is going to be a diagonal matrix. And the first element is going to be lambda1, which is the largest eigenvalue of your covariance matrix Cx. Next element is going to be lambda2 and all the way up to lambda n. So what does it mean? It means that in the transformed space, in the Y space, your transformed features or transformed vectors are not correlated. That's why the covariance matrix is a diagonal matrix. All right. So that is an important concept or an important point. That is, what does PCA do? It takes X space and moves into a Y space such that in the new space, there is no correlation among different components of the vectors in the new space. So that's why if you were to calculate the covariance matrix in the transformed space, it will be a diagonal matrix. All right. Now, let us say that we are interested in reducing the number of dimensions. So our original number of dimensions is small n, because each starting vector was an n-dimensional vector. All right. In the transformed space, if we do not discard any eigenvectors and any eigenvalues, then we will have n-dimensional transformed space. The only difference between the two spaces will be that in the transformed space, the components will be uncorrelated. But our interest is one more thing there, and that is we want to reduce the number of dimensions. So let us say we want to keep only p dimensions in the transformed space where p is less than n. So we will do that by just keeping the first p rows of matrix A, and we will discard the rest of the rows. So if we use only first p rows of matrix A and apply that transformation to vector X, obviously the resulting vectors will be p-dimensional. So you will be getting dimensionality reduction. All right. Now, anytime you reduce the number of dimensions or you perform some kind of approximation, there is going to be loss of information, or you can say there will be some approximation error, which will be resulting as you apply the transformation. So it can be shown or it can be proved, and we are not going to do the derivations, but people have done it, and they have shown that if you look at the mean square error of approximation, then that mean square error of approximation is equal to sum of all the eigenvalues that have been discarded. So if you look at the equation, our index for eigenvalues is changing from j equal to p plus 1 to all the way up to n. Why? Because we are keeping the first p eigenvalues and corresponding eigenvectors in our matrix A. rest of them are being discarded. So the sum of all the eigenvalues that have been discarded, that sum gives you the amount of mean square error or amount of approximation error that is taking place. All right. Another way to represent the approximation is to take the ratio of the discarded sum of eigenvalues divided by the sum of all the eigenvalues. So if you are discarding 10%, that means you are getting a 10% approximation error. Okay. Now, the best results for PCA are obtained in those situations where the original data has a lot of correlation. If your starting set of if your starting set of data vectors do not have any correlation, then PCA will not be able to help you much, because PCA is trying to transform the data so that it doesn't have correlation. But if your data already has no correlation, then there is nothing for PCA to do. All right. So PCA is going to give you dimensionality reduction only in those situations where the data shows some correlation among different features. All right. So that's an important point. So with that, let's take an example. So let us say that in this top corner, we have 10 observations or 10 data vectors. Each vector is a three-dimensional vector. For example, the first vector is 7, 4, 3. The second one is 4, 1, 8, and so on and so on. All right. So we are given 10 vectors, each vector with 3 components. What we like to do is we will like to apply PCA and reduce the data into 2 dimensions. All right. Now, if you go back and look at the equation where we are applying transformation through matrix A that we construct using eigenvectors, in that transformation, we are subtracting our original vectors from the mean vector. All right. So the first thing we need to do is to calculate the mean vector for the data. So if you take the mean vector for these 10 examples, basically that mean vector is going to be 6.9, 3.5, and 5.1. That's the average over each column. All right. Now with the mean vector, what we can do is we can calculate the covariance matrix. All right. So if you do that calculation, your sample covariance matrix is going to look like as shown over here. So the first component is going to be 2.32, second component 1.61, and then minus 0.433. And similarly, you have the second row and third. All right. So basically, we have started with the data, we got the mean vector, we got the covariance matrix. So now in order to construct matrix A for applying the transformation, what we need to do is we need to calculate the eigenvalues and eigenvectors of this covariance matrix. So if we calculate the eigenvalues, and those eigenvalues come out to be 8.274, 3.676, and 0.749. So you can see that the first 2 eigenvalues are pretty large. The first eigenvalue, 8.27, is about 10 times or more than 10 times than the third or the lowest eigenvalue. All right. And the second eigenvalue is also about 5 times more than the lowest eigenvalue. All right. Now, corresponding to these eigenvalues, we get the 3 eigenvectors. So these vectors are shown in the column form. So the first eigenvector is 0.013, 0.25 and then minus 0.95 and so on and so forth. All right. So what we can do is we can discard or ignore the third eigenvector and the third eigenvalue because we want to approximate or represent the data into 2 dimensions. So we will throw away the smallest eigenvalue and the eigenvector corresponding to that. All right. So with that, you will end up with a matrix A, which has 2 rows and 3 columns. The first row is made up of the first eigenvector. The second row is made up of the second eigenvector. All right. So with that matrix A, you can now apply the formula for doing the transformation. And once you do the transformation, you will end up with the mapped or transformed values for your vectors. So you can see here, I'm showing you 2-dimensional mapping of the original data using 2 eigenvectors. So the first point from 3 dimensions, when it is mapped to 2 dimensions, has a value of 2.15 and 0.173 and so on and so forth. All right. Now what we can do is we can try to figure out what is the approximation error. All right. And in order to calculate the approximation error, what we will do is we will try to go back from 2 dimension to 3 dimension and recover our original data. And what will happen is, since we discarded the smallest eigenvalue and corresponding eigenvectors, so when we go back now from 2 dimension to 3 dimension, our data that we reconstruct is not going to be identical to the original data. It is going to be little different. And that difference is what we call as the approximation error, or what is the mean square error between the original data and the reconstructed data. All right. So let's look at the next slide. So what we have done is we have reconstructed the data. To do the reconstruction, again, you can use the same equation and you can just move the things around and you'll do the reconstruction. All right. So reconstructed data is shown here. And at the bottom in the yellow box, I'm showing you the original data. So let us just look at the first vector. So our original first vector was 7, 4, and 3. But when we reconstruct it, it is 7.08, 3.92, and 2.99. That means it's not same as original, but it's pretty close. All right. So we can actually calculate the mean square error between the original data and the reconstructed data, point by point or data by data. And that reconstructed error comes out to be 0.674. All right. Now, if I divide 0.674, or if I multiply it with 0.9, I get 674, which is same as the smallest eigenvalue. All right. That means my mean square error is same as the smallest eigenvalue. Now you will notice here that in the first line, I'm writing mean square error as 0.0674. And then in the second equation, instead of taking just the eigenvalue, I'm actually multiplying that eigenvalue with 0.9, and I'm saying, all right, that is equal to 0.674, which is your mean square error. The reason I'm doing 9 by 10 is, if you look at the formula for sample mean and sample covariance matrices, you will come across 2 formulas. In some cases, you will find people writing 1 divided by capital N. And in some cases, people write 1 divided by capital N minus 1. Now, when N is very large, it doesn't matter whether you have 1 by N or 1 by n minus 1. But when capital N, that is the number of samples, is not very large, then whether you are using 1 by n or 1 by n minus 1, that can make a difference. So that's why I'm multiplying it by 9 by 10, because I'm using 1 by n, but I should have used 1 by n minus 1. So to correct for that, that's why I'm doing that. And that's why you end up with 0.674 as the mean square error, as well as eigenvalue 3 multiplied with that gives you 0.67. All right. So this was done. I didn't show you the whole set of calculations, but this was implemented using Excel. So you can actually do PCA using Excel. But what we like to do is to do it using Python. All right. So let us take the same example and run it through our Python. All right. So we'll basically import NumPy. From NumPy, we will be making use of a library called a linear algebra library. So we will import that as LA. And to do the plotting, we will import the matplot library. All right. So those are the three things we need. So if you look at the next cell, we are defining X as an n-dimensional array. In this case, it's a 3-dimensional array. And we have 10 readings or 10 elements or 10 vectors. And I have written them out here. And you can see that these numbers are same as in the previous example. All right. So we are trying to do the same example, but using now Python and library. All right. So we have defined the array. Now we can calculate the mean. So we get the X mean. So X mean is 6.9, 3.5, 5.1. Once we got the mean, we need to get the covariance matrix. So now we can make use of this linear algebra library. And sorry, we don't need actually here for the covariance matrix. So we can calculate the covariance matrix as shown, and we get the covariance matrix result. All right. Now what we need is, once we have the covariance matrix, we need to get eigenvalues and eigenvectors. So that is where we make use of the linear algebra library. And that library allows us to get the eigenvectors and eigenvalues. So the statements for calculating the eigenvalues and eigenvectors are shown here. And basically we get 3 eigenvalues. In this case, they are printed from smallest to highest. And then we get the corresponding eigenvectors. All right. So you can see that these numbers are similar to what we had obtained earlier. And then we can form a transformation matrix by keeping only 2 eigenvectors that correspond to our highest and next highest eigenvalues. All right. So using those 2 eigenvectors, we define our matrix A, which we will use in the transformation. So that matrix A is shown here. And once we have that matrix A, we can apply the actual transformation to calculate the y vectors. So basically, you can see here that is what we are doing, and we are getting the y vector. All right. So we have a 2-dimensional mapping of our 3-dimensional data. Our interest is to see how close these vectors will be when we reconstruct them. So let us apply the reconstruction. So basically, let's calculate what we call as X hat, which indicates the reconstructed vectors. All right. So we recover them and of course add mean, and that basically gives you a set of reconstructed vectors. So again, you can see that these vectors are pretty close to the original vectors, but they are not identical. And the numbers are similar to what we had received earlier. All right. So again, we can calculate the mean square error. And that error comes out to be 0.674, which is again same as the lowest eigenvalue that we discarded. All right. Now, if you want to see visually how the original vectors and the reconstructed vectors match each other. So what we have done here is we have plotted the original vectors in the pink and the corresponding reconstructed values in the green. So these are 10 bar plots, one for each three-dimensional vector in the original data set. All right, so you can see that the green and pink bars are pretty close to each other. All right, there are only minor differences. That means in this particular case, we are able to get a decent approximation in 2 dimensions with our data. All right, any question? All right. Now, what I showed you was doing PCA calculations where you wrote down the code for calculating the covariance matrix, you wrote down the function for finding the mean and then applying the transformation, creating the matrix A and so on and so forth. All right. In practice, if you are using sklearn library, then you don't even need to worry about those steps. sklearn library has a built-in PCA function that you can use. So basically, if you look at it from sklearn library, we will import decomposition, because that is the name for PCA and other decomposition methods that are part of sklearn library. All right. So we will define our PCA method as decomposition.pca, and we can specify how many components we want to keep. So in this case, we want to keep only 2 components. All right. So we say number of components is 2. So what we have done is we have specified we want to apply PCA and we want to get the results in 2 dimensions. All right. So next step is, and this step is pretty similar to everything you do in sklearn. That is, whatever you want to do, in this case, you want to apply PCA. So PCA dot fit, and of course you want to fit this using the data that you have. So in this case, the data is our array that we defined on the previous slide, X. So basically we say, all right, we want to fit PCA to X. All right. So what this step will do is internally sklearn will calculate the mean vector, covariance matrix, eigenvalues, eigenvectors, form the matrix A and all that. So all those things that you did in the last slide, sklearn will do it for you. You don't need to worry about that. All right. All you do is in the next line, you write down, give me my Y vectors by applying this PCA transformation. So basically you say Y equal to PCA dot transform. And of course, you're transforming X. So transform X. And that's it. And then you can look at your Y vector. So basically, you are done. So sklearn library makes it so easy, so convenient that you can do PCA in just 2 lines. All right. And of course, if you want to go back and reconstruct, then at the bottom, you can see I'm showing you, you can apply the inverse transform to do the reconstruction. And again, sklearn will do that. You can calculate the mean square error and you end up with the same result. All right. So it's very easy to do it, but the point is you must understand the steps. If you don't understand what you are doing or what PCA is doing, then you will be applying it blindly. And sometimes the results you will get will be useful to you. Sometimes the results you will get may not be that useful to you. All right. So keep that in mind. All right. So let's move on. So let's look at one or two other examples of PCA. Okay, all you need to do is to now you know how to apply it. So let's look at a couple of examples and see if there are any other issues or any other points to remember. All right. So this illustration of PCA is on a data set which is known as wine data set. You can actually download this data set from UCI Irvine library. And I think this data set is also part of sklearn library. So you can actually use this data set in the sklearn library to do whatever you want to do. All right. So in this case, this data set has three categories. That is, there are three kinds of wines or three qualities of wine in this data set. And the quality is being measured or defined in terms of 13 attributes or 13 characteristics. And basically, they have 178 examples. So each example is a 13-dimensional vector of measurements, and then there is a dependent or a class label that says whether it's wine of quality 1 or quality 2 or quality 3. All right. So if you look at the scatter plot, this is how the scatter plot will look like for some of the features of the wine data. All right. Because if you want to look at all possible pairs, then it will be a 13 by 13 pairs of plots. And obviously, we'll not be able to fit all of them on one sheet. So basically, I'm showing you only a scatter plot for some of the features or some of the pairs of features. All right. Now we take this wine data and apply PCA. So when we apply PCA to this wine data, there are 13 features. So our covariance matrix is going to be a 13 by 13 matrix. And when we calculate the eigenvalues and eigenvectors, we will be getting 13 eigenvalues. So if you make a plot of those eigenvalues, that is on the vertical axis, you have the eigenvalue, and on the x-axis, you number them as eigenvalue 1, 2, 3, etc. And remember, the convention is the highest eigenvalue gets number 1. The next highest is index 2, and so on. All right. So that's why you see we are going down from 1 to 10. All right. So I'm showing you 10 eigenvalues. And also I have listed actually all 13 on the chart. All right. So you can see that we start off with a very high eigenvalue, 4.7. Next eigenvalue is 2.49, and so on and so forth. And after a couple of eigenvalues, their values start falling. All right. And we can see that from the graph. All right. You can see here that somewhere around eigenvalue number 4, there is a knee point. That is, if you look at this graph, you can approximate this graph in terms of two linear segments. One segment going up from 0.4 to the point representing first eigenvalue. So one can approximate that through a single line. And then from 0.4 all the way up to 0.10, we can draw another single line. All right. So basically, the 0.4, the eigenvalue at location 4 is kind of serving as a knee point. So typically what people do is when they make a plot like this, they try to locate the knee point. And all the eigenvalues to the left of knee point are typically used in the representation in the lower dimensional space. All the eigenvalues to the right of knee points are generally thrown away or discarded. All right. So if you follow that logic, you can say that this data can be transformed from a 13-dimensional space to a 4-dimensional space. The other point that you need to remember is and it is mentioned here that the results are obtained after normalizing all features to zero mean and unit variance. So remember, I mentioned earlier when we were talking about the distance that it is a very good idea, very good practice to normalize data. So that way, no particular feature will dominate the calculations. All right. So again, we have done that. And after doing that, only we have done the calculations for finding the eigenvalues and eigenvectors. All right. If you just take top two eigenvalues and top two corresponding eigenvectors and look at only in 2 dimensions for this wine data and try to plot it, that plot is going to look something like this. And next to every point, we have a number, either 1, 2, or 3. Okay. Those numbers are representing the label or the class indication for the corresponding point. All right. So you can see that the points that are marked with 2 are more or less quite different from points marked 1 or marked 3. They are all lying at different places. All right. So what this plot is telling us is that even in 2 dimensions, we can get a fairly good separation between 3 different classes of wines by just using first 2 features in the transform space. All right. So that is what this plot shows. All right. Any question? We have some more results just to give you an idea. So here is a data set. There is a data set of binary images for doing handwritten digit recognition. So here is just an example of how these handwritten digits look like in this data set. So let us take all the 3s. So what we have done is we have collected digit 3 writings written by lots of different people so that there is a variation in 3s written by different people. All right. So all those digits become our starting collection of data vectors. And what we'll do is we will take the mean, covariance matrix, get the eigenvalues, etc., etc. All right. So if you look at the digits or the pictures shown in the top row, so the first one is all blue, which shows you the mean. So if you take the mean of all these digits, that's how the mean 3 will look like. All right. If you look at the first eigenvalue and the first eigenvector, now in this case, the eigenvector is going to look like digit 3. So once you have all those values and you line them up in the form of a matrix, that matrix is going to take a shape similar to 3. All right. So the first eigenvalue, lambda 1, is 3.4 to the power 10 to the power 5. That means a very, very high eigenvalue. And the corresponding eigenvector is shown here. The blue areas represent positive values. So more blue means more positive. White is 0. And yellow represents negative values. So more negative means more yellow, less negative means less yellow. So what we have done is we have kind of plotted the first 4 eigenvectors for this particular collection of examples. All right. And for this data set, if you were to get all the eigenvectors and again make a plot of eigenvalues as you move from index 1 to index 2 and so on and so forth, again you can see that this plot is showing a nice decay. That is after some initial number of eigenvalues, in this case maybe about 10, 15, rest of the eigenvalues are falling very rapidly, and very quickly after 40th or so, most of the eigenvalues are really very small. So again, if one wants, one can take this data and transform it into a lower dimensional space. All right. And if you were to plot again some of these digits in 2 dimensions, just keeping 2 eigenvalues and then mapping them into 2-dimensional space, this is how many of these data points will get mapped. So again, you can see that there is, even with 2 features, you can get a decent separation, not a very good separation, but reasonably okay separation. So that is what is shown here. Now, what we have shown so far is how to use PCA when capital N is less than D. What does it mean? Capital N is the number of data vectors or number of examples that you have for doing your PCA. And D, small d, represents the size of the vector. So suppose you have thousands of images, okay? Let us say each image is a 30 by 30 image, all right? So you have 900 dimensions, all right? 30 by 30 is 900, all right? And let us say you have only 100 images. That means your capital N is 100 and your dimension is 900. If you look back at what we did earlier, we typically had more examples than the number of dimensions. All right. So in certain situations, you will have a case where you will have fewer examples, but those examples are in a very high dimensional space. So in such cases, a straightforward application of PCA is not going to work out. The reason it's not going to work out is because you will not be able to get the eigenvalues and eigenvectors, because you will run into the issue of determinant being equal to 0 and so on and so forth. So in situations where direct straightforward application of PCA using covariance matrix is not possible, because you have fewer examples and a larger dimensionality, what you need to do is to make use of another technique, which is known as SVD, or Singular Value Decomposition. And that is the one that one has to resort to find the eigenvalues and eigenvectors for situations where you have fewer examples and a higher dimensional space. All right. So let us see what is SVD. So SVD, as I said, stands for Singular Value Decomposition. It's a technique for handling matrices or sets of equations that do not have an inverse. Because if you have a rectangular matrix, you cannot define an inverse of a rectangular matrix. All right. The inverse of a matrix exists only when you have a square matrix, and that too when the square matrix doesn't have a determinant equal to 0. All right. So basically, there are situations where you might come across something like this. It doesn't mean that in those situations you cannot do dimensionality reduction. What it means is that in those situations, you need to follow SVD rather than following PCA. So let us see what are the other points. So SVD is a handy mathematical technique that has numerous applications to numerous situations. What does SVD say? according to singular value decomposition, it says that you can take any arbitrary matrix F, and let us say this matrix is of size m by n. M is the number of rows, n is the number of columns. Then this arbitrary rectangular matrix F can be decomposed or can be expressed as matrix U transpose matrix F matrix V equal to lambda matrix lambda to the power 1 by 2. What are these U and V matrices? U and V are orthogonal matrices of size m by m and size n by n respectively. And the matrix lambda is an m by n diagonal matrix as shown here. So it is a diagonal matrix of lambda 1 square root, lambda 2 square root, so on, going all the way up to lambda r, and then rest of the diagonal values are 0. All right. So that's what SVD tells us, that it says you can take any matrix F of arbitrary size, and through U and V matrices, you can actually represent that matrix F through this relationship. So let us see how we take advantage of this relationship to do the dimensionality reduction. But before we do that, let's just take an example. So, and of course, before moving on to the example, let's also look at one or two other points related to SVD. So based on the previous equation, if you flip the things around, you can say that we can also write matrix F equal to matrix U lambda to the power 1 by 2 multiplied by V transpose. So basically, if we know matrix U, we know matrix V, and we know matrix lambda, we can express or we can get back our matrix F. Now, the columns of matrix U, how do we form these matrices? So that's what we are showing here. So the columns of matrix U are composed of the eigenvectors of symmetric matrix F transpose. So you start with matrix F, and what you can do it by taking the matrix product F transpose, you end up with a symmetric matrix. And for that symmetric matrix, you can do the eigenvectors and eigenvalues. Similarly, you can take matrix F transpose F, which is again going to be a symmetric matrix, and extract its eigenvectors. And you will use those eigenvectors to form matrix V. And once you know how to form matrix U and V, basically you can decompose matrix F in whichever way you want. All right. So in terms of eigenvectors, it's possible to express matrix F as follows. That is, matrix F can be represented as a summation of outer products of vectors Uj and Vj transpose. And these outer products are weighted by corresponding singular values or lambda values. These values are called singular values, and that's why this method is called singular value decomposition. So the outer products of the eigenvectors from above form a set of unit rank matrices, which can be scaled by corresponding singular values of F, or which can be weighted by corresponding singular values of F. And as mentioned earlier, the diagonal elements of lambda matrix are called singular values of matrix A. Oh, sorry, it should be matrix F because that is what we were using earlier. And if A is singular, some of the diagonal elements will be 0. All right. So in general, the rank A is number of non-zero diagonal elements of lambda matrix. All right. Let's come to an example that will help you understand what we are talking about. All right. So let's take an example here. So we are given a matrix F, which has 4 rows and 2 columns. All right. Obviously, there is no inverse of this matrix. We cannot really do anything. So what we will do is we will calculate matrix V, and matrix V will be calculated using F transpose F. So we take matrix F, we take its transpose, and then multiply that transpose to matrix F. So that will give us a 2 by 2 matrix. So in this case, we have a 2 by 2 matrix. And what we can do is we can calculate its eigenvalues and its eigenvectors. So if you do those calculations, you will find that the eigenvalues of this matrix are 125, and the corresponding eigenvectors are as shown. All right. Let's calculate matrix U. Matrix U will be calculated doing the matrix multiplication F transpose. All right. So matrix U will turn out to be a 4 by 4 matrix. And this matrix, if we again calculate its eigenvalues and eigenvectors, you will find that this matrix has only 2 non-zero eigenvalues. And those 2 non-zero eigenvalues happen to be same as the ones we saw earlier, that is 125. The other 2 eigenvalues are 0. And the corresponding eigenvectors for the eigenvalues 125 are as given. All right. So what we have done is we have calculated matrix V, we have calculated matrix U, we've gotten their eigenvalues, we gotten their eigenvectors. Now what we can do is we can express our matrix F as an outer product of these eigenvectors and sum those outer products with the corresponding weights, which come as the square roots of the singular values. So if you look at the calculations here, so the first singular value is 100, its square root will be 10. So 100 is square root, and then multiply those 2 eigenvectors. You end up with a 4 by 2 matrix. Then you take the second eigenvalue, 25 square root, again perform the corresponding eigenvector multiplications. You get another 4 by 2 matrix, and you add them up, and you find that basically the result is identical to your matrix F. All right. So basically what SVD is telling you is that even if you have a rectangular matrix, or even if you have a situation where you have more features and fewer examples, it is possible to do the decomposition. All right. Now in this case, we had 2 eigenvalues and 2 non-zero eigenvalues. All right. So, and we used both of them to do the to reconstruct our matrix F. All right. And since we did not throw away any eigenvalues or eigenvectors, our matrix F looks exactly the same as the original matrix F. All right. Suppose you had thrown away the eigenvalue that corresponds to a singular value of 25. All right. Then your matrix F is going to look like only the first 4 by 2 matrix in the expression at the bottom. The second expression will not be there because you have discarded that. All right. And that will give you, you can see, an approximation. So instead of 6, you will get 5.04. Instead of 6 in the second column, you will get 6.72. So you are getting an approximation. So again, by discarding some of the singular values, you can get the dimensionality reduction or approximation to your data. So that is how the SVD, or singular value decomposition, works. So typically people like to illustrate SVD through this picture, which basically shows you that F matrix could be a square matrix with more rows and fewer columns. If that is the case, then U matrix is going to be a bigger matrix and V matrix is going to be a smaller matrix. On the other hand, if F matrix has more columns and fewer rows, then your U matrix is going to be a smaller matrix and V matrix is going to be a bigger matrix. All right. So just showed you how things will look like. Now, if you were to do approximation using SVD, so you started with one matrix and you went through all the process and you discarded some eigenvalues and eigenvectors and you reconstructed a new matrix. And new matrix is going to be a little different from the original matrix. So just like we defined the mean square error earlier for the PCA, we can define the error again. And in this case, we can say what is the similarity or the error between the original matrix and the reconstructed matrix. So a common definition for measuring this similarity or difference is known as the Frobenius norm. And the Frobenius norm is defined as shown in the expression, where Fij square is the difference between the elements at the row I and column j between the original and the reconstructed matrix. And again, similar to the PCA results, it can be shown that there is a relationship between this Frobenius norm and these singular values or the eigenvalues that you get. All right. So one can look at how much a matrix will change by looking at the eigenvalues or the singular values that you are throwing away. All right. So let's look at an approximation. So as I said, this is how you will be doing the approximation. So you will calculate an approximated matrix F hat using this formula, where you are keeping only the k singular values and corresponding m by n rank 1 matrices. You are throwing away everything else. So that's how you will reconstruct the approximate matrix. And the error in the approximation will be given by this formula. So you take the difference and use that as an error. Okay. And again, just like PCA, it's possible to show that the squared error will be again sum of all the eigenvalues that will be thrown away. Okay. Here is an example of data reduction using SVD. All right. For example, as I said, suppose you have only one picture, like the one I have in the leftmost picture. All right. Now, with one picture, you cannot do any PCA, because for PCA, you need a large number of examples. All right. So you can say that you have only one vector, and the size of the vector is the size of the picture. That is, if this picture has 100 rows and 100 columns, then the size of the vector is 100 by 100, and I have only one example. What SVD tells us that it doesn't matter you have this situation or not, you can still do an approximation. So if you look at your original picture as a matrix F, what we can do is we can follow all the steps that I showed you and calculate U matrices, V matrices, all the singular values, and then try to reconstruct the original matrix by keeping only certain number of singular values. All right. So that is what I'm showing you here. So if you look at the second picture, that second picture is reconstructed using only 32 singular values. All right. The next picture is reconstructed only 16 singular values or eigenvalues. And finally, it's reconstructed only using 8 eigenvalues and corresponding eigenvectors. So you can see that the last picture obviously is highly approximated because you can see all the differences with the original picture. But between the first and second, it's really difficult to make out how much is the difference. All right. So you can see that SVD can be used for dimensionality reduction, for data approximation, by keeping only fewer eigenvalues and eigenvectors and discarding the rest of them. All right. So that is really what SVD allows you to do. So this idea of SVD, I did mention the eigenfaces last time. So the eigenfaces were not calculated using PCA because you are working with pictures there. So if you have a picture of size 128 by 128, even if you assume, basically you have 128 times 128 dimensions. So you need to collect then many more examples to apply PCA, and that may not be possible because that's too many pictures. So if you have fewer pictures and you still want to do this, all you need to do is to apply SVD. All right, so somebody did that and they called the resulting pictures as eigenfaces. All right, so basically that is what we are showing here. So basically, given a collection of pictures, we can extract the eigenvectors, eigenfaces, and then we can represent any picture as a summation of different eigenfaces, each weighted by certain weight value. All right. And those weight values are different for different pictures. The basis vectors or the eigenfaces remain the same. All right. So that's an example of SVD, and I did mention that earlier, and how it can be used for storing IDs and things like that. All right. So anytime you apply PCA or you apply SVD, the question is how many eigenvalues I should keep. And the answer is similar to what I mentioned earlier. That is, you basically make a plot of all the eigenvalues as they are falling and try to locate a point which you can call as a knee point where things start falling much more rapidly. So basically up to the knee point, you can keep all the eigenvalues and eigenvectors and throw away the rest of them. Or you can look at the ratio of eigenvalues, sum of eigenvalues that you're discarding divided by the sum of all the eigenvalues, and that tells you how much error you are introducing. All right, so that's basically what is shown in this slide. All right, so let us summarize PCA/SVD. So PCA is a good technique for data reduction. Now remember, PCA may or may not provide good results for classification. If you're trying to build a classification model, it's not necessary that PCA will give you good results, because PCA is geared for data reduction or data approximation, and it does not make use of any class label information. That means PCA is independent of whatever is the category of the underlying data vectors. All right. So it may give you good results for classification. It may not give you good results for classification. All right. Now there are methods which do take into account the class label while doing the dimensionality reduction. The examples of such methods are what we call as Fisher's discriminant function, supervised PCA. There is a version of PCA known as the supervised PCA. Canonical correlation analysis stands for CCA, and partial least squares method. These are some of the methods that work with taking into account class labels. Out of these, we will be looking at the Fisher's discriminant function method later on. The other ones we will not discuss. All right. They are a little more advanced and we cannot cover everything. All right. PCA is good for linear problem. Remember, matrix A is a linear transformation. All right. So PCA is good for linear problems only. Sometimes if you're dealing with data which is highly nonlinear, kernel PCA is used sometimes. And again, we will not cover kernel PCA. All right. And finally, remember, it's a good practice to normalize data before applying PCA. All right. So any question that takes care of PCA and SVD for dimensionality reduction, we are going to be looking at one or two other methods. So if you have any question at this point, let me know. All right, let's look at another way of looking at dimensionality reduction. See, what we did so far in PCA or SVD is that we try to transform data or approximate data by doing some kind of matrix factorization. Another way is, if I have 13 features and I want to get 5 features, maybe I can discard 8 features and just keep 5 features. All right. Question is, how do I know which particular combination of 5 features is to be kept and what are those 8 features that should be discarded? All right. So in the PCA, we are transforming the features to do the reduction. In this method, we do not do any transformation. We just try to figure out what is the best subset of features that can be used in place of all the features. All right. So this is known as dimensionality reduction via feature subset selection. So the idea here is to select a subset of k features out of n original features. All right. Obviously, if you have n original features and you want to pick k, there are a number of ways in which you can do that. And the number of possible ways in this particular case is factorial n divided by factorial k times factorial n minus k. All right. So if you take n equal to 20 and k equal to 5 and plug in the numbers, you find that the number of possible subsets is 15,504. That means so many different possibilities are there. And what we need to do is to pick one possibility out of those possibilities, which is the best possibility. All right. That means we need to do some kind of search. We need to go over these combinations and figure out which is the best combination. All right. Now, when the number of possibilities is small, then one can do what we call as an exhaustive search. That is, you can go over every possibility one by one and see how good is that. But for an example like this or any other similar example, the number of possibilities is going to be very large. So exhaustive search may not be a good idea to proceed. So what you want to do is you want to have some kind of trick that tells you which particular combination is really a good combination. All right. So what one can do is one can kind of think of an approach like this. So you start at the bottom left with the attributes, and you have some method, let's call it as a search strategy, which picks k attributes or defines what is the subset you want to pick. So you pick the subset. And then you need to have some kind of method that tells you how good is that subset. So you have an evaluation criteria, all right? And as you go over different possible subsets, at some point you need to stop. Otherwise, you will keep on going through your search process, all right? So you define some kind of stopping criterion. And once you hit that, you can say that you have selected your subset, all right? So this is an approach which we call as the feature subset selection approach or feature subset selection process. So there are two components, important components in this process. Number one, a way to figure out how to pick a subset. And number two, how to do an evaluation of a given subset. How to figure out whether a given subset is really good or not, all right? So what we need to do is we need to have some kind of measure which tells us whether a subset is good or not. And suppose we are doing this subset selection to build classification models. In that case, what we can do is we can use a evaluation metric that will tell us whether this subset is good for classification model or not. And if it is good, we will keep it. If it is not good, we'll discard it. All right. So there are two possible measures. One could create their own new measures, but we will discuss only two of them here. One is known as the divergence, and the other one is known as scatter matrices based measures. All right. So we will look at these two measures now. And the idea of divergence is related to the idea of entropy, which I think I mentioned in one of the earlier lectures, but let us take a look at it again. So entropy is a measure of uncertainty. A system with no uncertainty has zero entropy. And if a system has a lot of uncertainty, then its entropy value is very high, all right? So to define how we measure entropy, let us consider a situation where there are n possible outcomes of an event. So there is some phenomenon that takes place, and there are n possibilities that could occur as a result of that phenomenon, or n possible outcomes. And let P sub I indicate the probability that the outcome is going to be the ith outcome. All right. So every outcome has a different probability. In that case, we can say, all right, the entropy of this phenomena or event is given by minus sum of I equal to 1 to n pi log pi. Or you can write it also as summation pi log 1 upon pi, if you don't want to carry the negatives. All right. So this is the definition of entropy. And the divergence idea is based on this definition. But before we go that, again, let's look at one more slide on entropy. So the entropy H is 0 if and only if exactly one event has a possibility of 1. That is, if the phenomena has only one outcome, then entropy is 0. All right. Entropy H has a maximum value if all possible outcomes have equal probability. So if you have n possible outcomes and each and every outcome has an equal probability, then entropy maximum. For example, if you have a coin and the coin is not manipulated or biased, obviously when you toss the coin, either it can be head or tail, all right? Both have equal probability. So you can say the entropy of tossing a coin and observing a head or tail, that entropy is maximum equal to 1. All right. And of course, if you look at two events, event X and event Y, then the joint entropy of two events is less than or equal to the sum of individual entropies. All right. So those are some of the things you need to remember. Let's look at what we mean by divergence, which is also known as what we call as cross entropy. So suppose we are given two discrete probability distributions. Then KL divergence, which stands for Kullback and Liberal divergence, it measures the similarity of these two probability distributions. All right. Now, instead of saying two probability distributions, let us say we have two different events. Event number one has certain possibilities, and each possibility has a corresponding probability. Event number two has certain possibilities and has corresponding probability. All right. And let's say both events have 5 possible outcomes, but the corresponding probabilities are different. All right. Then one might say, well, how similar are these two events? Okay. That is what basically we are trying to measure here in terms of two discrete probability distributions. All right. So KL divergence measures that. So KL divergence says, all right, the divergence between P and Q, or given Q, divergence for P is given by this expression Pi log Pi divided by Qi. All right. This is also known as I said, is cross entropy. All right. You can see that this is a non-negative and zero if and only if Pi is equal to Qi for all I values. All right. Otherwise, it's not equal to 0. All right. Other thing is the way we have defined it, you can see that if I interchange Q and P on the left hand side, then obviously the formula on the right hand side will change. All right. Then we will have to switch between P and Q on the right hand side also. All right. That means this measure is not a symmetric measure. That is, when you measure from P to Q or Q to P, you will end up with different results. All right. Typically, what we want P to Q or Q to P should give us similar outcome. So what one can do is one can take P to Q and Q to P formulas and add them up. That way, it doesn't matter whether you measure from P to Q or Q to P, you will end up with the same result. All right. So that is how we define Kullback and Liberal divergence. This is the formula for that in the case of discrete probabilities. Here is an example. So let's say that we have two phenomena. Both of them have 3 possible outcomes, 0, 1, and 2. The probabilities for these outcomes are different in the two phenomena. So the first one is 0.36, 0.48, and 0.16. In the second case, 0.333, 0.333, 0.333. All right. So we can now calculate what is the divergence. All right. And so P to Q and Q to P can be calculated as I shown you in the calculations. And if you want a symmetric result, then all you need to do is to add them up and divide by 2 if you want. All right. So that's how this divergence is measured. All right. In many cases, we are dealing with normal or Gaussian distributions. So in such cases, one can derive in the closed form a formula for measuring this divergence. So given two Gaussian or normal distributions with corresponding means as M1 and M2 and corresponding covariance matrices as C1 and C2, the formula for divergence is as shown. All right. And I think there is an example here. shown. So if I have mean vector 3, 3, second mean vector 2.3, 2.3, covariance matrix is diagonal with 0.2 in the first case and diagonal with 1.9 in the second case. What is the value of DKL? We can calculate it, or we can go to our libraries in Python and do the calculation. So basically the calculation is shown here. Basically all I have done is I have plugged in that formula and calculated the result. All right, so that's how one can calculate the divergence. All right, let us see where we are. Okay. Another measure to check how good is a particular subset of features is through what we call as a scatter matrices based measure. All right. So there is a concept of class scatter matrix, which is pretty similar to a covariance matrix, except that in the covariance matrix, you have a division 1 by n minus 1, which is not here. All right. So class scatter matrix S of J is for all the examples that you have from the jth category or jth level. All right. So that matrix is defined as shown. And if you have only two classes, then for J1 and J2, you can define the respective formulas. All right. And then one can also define what we call as a within class scatter matrix, which is nothing but sum of two individual scatter matrices. One can also define between class scatter matrix, which is basically a measure of how far the two mean vectors are from each other. So you can see that SB is simply measuring, in some sense, how far the mean vectors are. All right. And one can also define what we call as a mixture scatter matrix, which is a sum of SW and SB. These three matrices are pretty useful in number of things, and they are also used in evaluating different features. And the way these matrices are used for evaluating different features is based on some of the properties of these matrices. So there is a measure called J1, which is defined as the trace of matrix SM divided by trace of matrix SW. Remember, trace of a matrix is nothing but the sum of diagonal elements. So basically, you do that, or J2, which is the trace of SM divided, determinant of matrix SM divided by determinant of matrix SW, or another criteria J3, which is nothing but trace of matrix SW inverse multiplied with SM. These measures take on high values when data from two classes are far away, can be separated easily. If they don't take high values, it means there is a lot of overlap in the data from two classes. So one can look at these numbers and get an idea whether a given subset of features is likely to give you good results or not. All right. So we will stop at this point. And what we will do is we will in the next class look at, okay, we have taken care of how to evaluate. Now question is, how do we figure out subsets that we should be evaluating? Is there some kind of strategy that we can use? So that is what we will work on in the next lecture, and whatever else is left under dimensionality reduction and visualization. All right, so we'll stop here. Thank you.
Professor?